All right, everyone. It is now week 3 of Meteorology 107 Severe and Hazardous Weather. This week, we're going to be starting off with scales of weather, and it's actually going to be a little bit different of a video schedule. I'm going to be pairing the first two videos together, so this is going to be one presentation split up over two videos talking about scales of weather. We'll also touch on the general circulation pattern that we see in the atmosphere when we talk about planetary scale in this first part of this two-part lecture. And then the second lecture or second pair of lecture videos will be moving on to a synoptic scale focus where we talk about air masses, fronts, and large scale systems. Now, in order to make those terms make sense, let's get into an overview of the scales of weather. So, if we just want to take a look at a picture of the state of weather around the globe, you have this kind of a plot that you would see from, say, the Earth null school site, where you have colors are displayed here are surface temperatures. The little streamline or particle tracers that you see are an illustration of the surface level wind. So we can see a lot of different things actually in this picture. We can see the warmest temperatures are over here, over the Sahara Desert. But in general, we have warm temperatures near the equator, slightly north of the equator, based on seasonality. And then it gets colder as we go towards the poles, since in this color table, our reds and oranges are warmer than our yellows, and then our greens, then our blues, and then our purple. So we get this general pattern, this warm to cold pattern that we can see as well. Plus, you can see some just broader scale flow here. You can see that here you have generally easterly wind because the wind is, even though there is some north-south component, it's generally coming from the east in this direction. And we also see things like these little swirls, actually they aren't all that little, these medium-sized swirls here and here. And if I were to be able to spin this globe around, you can see more on the other side as well. But then we get even smaller scale things than that. We get these temperature gradients, these smaller and tighter scale contrast in temperature. And then we also get these differences that are due to terrain and vegetation. So we have all these different phenomena from the very big scale of in the entire cross section of the hemisphere going from warm to cold, all the way down to these really local influences. And even there's things that we are important that we can't even see on this broad scale of a map, which brings us to sort of a perspective on what the scales of weather could be. That we'd have this width separation from really small scale things to very large scale things. And something I couldn't show you in that past diagram because it was just a static image is that we also have a time scale separation, that things that tend to be small also tend to be short-lived, and things that are large also tend to be long-lived. Luckily, this is a fairly tight tendency, so we can provide one scale separation to split up these phenomena based on both width and time. So meteorologists tend to categorize this into 4 different scales. So our smallest scale phenomena are typically considered things that are on scales of less than about 2 kilometers. And this includes things like tornadoes, dust devils, small scale clouds, and all that. And we call this microscale. Next up, bigger than that, is mesoscale. Then we have synoptic scale. And finally, planetary scale. This next chart is a similar way of looking at it, but we flip the axes. We now have our spatial scale, our distances, over here on the y-axis, and our time, lifespan, duration axes on the x-axis. And so you can see these sort of categories going from small scales with microscale up the categories to what it calls global scale, or we can refer to as planetary scale. So over the next 2 videos for this lecture, I'll be going from the largest scales all the way down to the small scales, trying to give an overview of what's important about all of them. So if we look at the planetary scale, I think a good place to look at the planetary scale is building up just the general long-term behavior of what the atmosphere does in its broadest sense. So if we go very back to the beginning, first videos of this course, talked about one of the big drivers of what makes the atmosphere work or do things is that the sun doesn't heat the earth the same everywhere because the earth is a sphere. So you get more direct solar radiation towards the equator and less direct or more steeply angled radiation towards the poles. This means that we heat up towards the equator more and we are cooler towards the poles. This in turn will set up a pattern. And the first sort of response to that differential heating that we have is we get pressure gradients showing up. So if we're just considering the Earth as a uniform sphere that's heated by the sun, we'll get pressure gradients showing up. Now, this isn't even talking about rotation yet, but we get high pressure where it's colder and low pressure where it's warmer in this sort of idealized sense. And we know from before again that wind or flow, movement of air, tends to come from pressure gradients. So we go from high pressure to low pressure. So we get this polar flow that's induced, polar flow meaning coming from the pole. And it sets up this kind of circulation that we have high pressure to low pressure. And because the air has to go somewhere, it can't just scrunch up infinitely at the equator. It has to return and go somewhere. So we get this sort of one-celled circulation in each hemisphere. So we get it looking like that. Of course, I said this is considering no rotation. But we know the Earth is spinning. It isn't just a sphere sitting in space. It's spinning around its axis. So that rotation tends to cause apparent deflections of the flow because momentum is conserved in the absolute or external reference frame. So when we're on an Earth that's spinning, it's going to look like our winds are being turned in a certain direction in order to maintain that conservation in the absolute reference frame. So we call this Coriolis force. And if you look above, hopefully I've linked a card to an explanational video or two if you want to go more in depth on Coriolis. Otherwise, it'll also be down in the description of this video below. I encourage you to check those out for more details. But the gist of it is that Coriolis force, due to the rotation of the Earth, tends to deflect flow or wind in the northern hemisphere to the right, and in the northern hemisphere again, and in the south to the left. So again, in our very simplified view, we now start getting this convergence along the equator from the flow that tends toward the poles, goes towards the equator, and turns and converges along the equator like this. The final thing in this picture is that because we have this flow going from high pressure to low pressure, but it's also going across temperature gradients, we end up, and because it's in a spinning reference frame when we get this deflection occurring, we get instability. So if there's any small imperfections, of course, if this was a perfect sphere, it would be just in a static, quasi-static pattern. But any little thing that's off, such as differences in heating or just straight turbulence, just random chaotic variations in the airflow, would create wave patterns and oscillations and things that would look like they're bouncing back and forth. So you create oscillations like this, which also, if we look, creates banding structures. The exact mathematics of how this works out, we're not going to worry about, But what's important to know is that the general circulation of the atmosphere ends up coming from differential heating. We get pressure gradients. We're on a rotating reference frame because the Earth is spinning. And then we get instability, which creates these wave patterns or these oscillations, and they create bands. Now this sort of just shows the first little portion of it. If we want the full picture of what this general circulation is, we go to this slide, where again, general circulation referring to the long-term average planetary flow. So what we'd expect to see in general, of course, allowing for variations, which we'll talk about later on. But if we were to follow this general circulation model, it would be a 3-cell conceptual model, where if we start at the ITCZ, which is the intertropical convergence zone, where we had the airflow coming together, that tends to create upward motion, which gives us storms. So it tends to show itself as a line of storms, as I'll show in just a little bit. And then it creates this first circulation called the Hadley cell, where we get upward flow near the equator. We get flow that goes away from the equator towards the poles, and then it sinks around 30 degrees latitude, and then it returns along the surface back to the equator. However, because of the Coriolis deflection, these trade winds end up becoming easterly, since we're deflecting to the right as we return to the equator, and to the left as we return to the equator in the southern hemisphere. Then we get to what's in between. Because of this sinking, we end up getting this zone of fast winds that develop at the very top of the atmosphere. It's called the subtropical jet. And then because we have this sinking air, as we'll get to later in the videos, that creates zones of high pressure where things tend to stagnate. We don't get storms, we just get clear and stagnation. That's where the term horse latitudes come on, because where a lot of ships in the old days where you had to sail under wind power, they had to lighten up their loads in order to keep moving. Then we get to the Ferrel cell, which is this next circulation over here. And these, again, because we have wind that's coming from the equator, because of the deflection, it tends to be westerly because of Coriolis deflection. And then we get to about 60 degrees latitude, where we get a polar front and the polar jet, which separates the Ferrel cell from the polar cell. And the polar cell is another circulation going this way. And this polar cell, if you ever heard the term polar vortex, this is the kind of thing that can shift around and bring very cold air down away from the pole when things move around. Of course, this is in the idealized view, so on average, it's always around the pole. But, as we'll get to, it isn't always that perfect in the real atmosphere. So, talking about some of those things in a little bit more detail, I have the ITCZ, or Intertropical Convergence Zone, and this is a persistent band of convective or precipitation due to updraft in the tropics. And it's on average near the equator, but it does shift north and south with the seasons. It doesn't precisely follow where the sun's directly overhead because it takes a little bit of time to overcome essentially thermal inertia of the atmosphere. So it tends to be where things are warmest in the broader scale sense. And it's important for this particular class that we talk more about mid-latitude severe and hazardous weather, because it can interact with hurricanes in their early steps of formation. But we won't be talking about the ITCZ itself in any real detail here. The other thing to keep in mind is that, and this goes back to with forming hurricanes, is that this too oscillates. If we look back, this is our idealized pattern on average, but in the real atmosphere, things tend to be a little bit more messy. And so when we get things that become messy in the atmosphere, they perturb or they get moved away from where we expect them to be. But then there's forces or different things in play that tend to want to move it back. And so that initial displacement of whatever it may be and return ends up creating wave-like patterns or oscillations. So the ITCZ does that. And so does the jet stream. Well, we talked about those jets in the upper atmosphere. And the jet stream really refers to bands or ribbons of localized high wind speeds in the upper atmosphere near the tropopause. And again, another linked video either up there or down there can go into some really good details about the jet stream if you're interested. And it, again, definitely oscillates in the real world atmosphere. And these oscillatory patterns of the jet stream correspond to what we call planetary waves, these broad scale wave-like patterns that we see in the upper atmosphere. And these play a really, really important role in how the weather around the globe behaves and the connections of weather from one place in the globe to another. And we'll talk about some of those things later on. Other things to talk about with these planetary waves and upper level flow associated, again, jet stream is where the winds are maxima, but these patterns persist even around that. And just to give some terminology here, they're organized into troughs, which are these downward or U-shaped patterns in the northern hemisphere. Again, things are flipped if you're in the southern hemisphere. And these correspond to lower pressure zones or lower height zones if you're on a constant pressure surface. So where it's lower in height means you're closer to the ground and your columns at lower pressure. Or the opposite, we have ridges, which are these sort of N-shaped areas where we have higher pressure or higher heights. And just on how the thermodynamics of it work out, troughs where we have lower pressure or heights tend to be colder. Ridges where we have higher pressure or height tend to be warmer. And these waves, these patterns around the atmosphere, as you might have noticed from this nice little animation on the previous slide, they vary over time in how many oscillations there are, their count or number, how fast they move, and also how deep they are, their strength or amplitude. And within this pattern, and within where the jet stream tends to fall in sort of the center of these in the uppermost portions of these patterns, we also get local maxima or local strong points of wind that we call jet streaks that can move along and slide around and look like they're just little things following the flow, even though they are wind itself. They're just the strongest portions of wind. And so as a terminology thing, we'll be talking about jet streaks later in the course. Just need to know that those are localized maximum points of wind within the jet stream. And one more point here, just talking about how this upper level flow behaves that will become important as we go on, is that this upper level flow, this wind tends to follow something called geostrophic balance. The exact terminology, you don't have to worry about where it comes from, just know geostrophic balance is what meteorologists call this flow that is, one, it's parallel to the height contours. So if you see all these wind barbs, they are following the direction of these solid lines, which are the height contours, that higher heights tend to be to the right. So in this case, that's, if we look over, say, the central US, our higher height values are to the south and our lower ones are to the north. And so we notice if we're following the flow, that means if we sort of are going, let's see, I make sure I'm following and going that way with it, it's to our right, the higher heights, and our lower heights are to our left. And the final point about geostrophic balance is that faster winds, you can sort of see these brighter colors, tend to occur where the height contours are closest together, where we have stronger gradients. So those are the 3 points that are important about geostrophic balance. The other thing, and just sort of understanding where this physically comes from, which we'll go into an explanation in the next part of this lecture, is that it's a force balance between two things. That's why we call it a geostrophic balance, is because our force from the pressure gradient, which would tend to force acceleration in this direction, and Coriolis, which always tries to apply a force to the right in the northern hemisphere. So if we have flow going this way, the force will tend to be down that way towards the south, these two things for geostrophic balanced flow are balanced and they cancel each other out, leaving no net acceleration. So if we were to look at a plot, this will become important for your discussion post, so I wanted to show an example of what this looks like. We can see what this pattern looks like around the whole northern hemisphere. Just to get yourself oriented, this is the US, this is Africa leading up to Europe, and then around here is Asia. So we end up seeing these wave patterns where over the continental US and over Canada, we have this nice broad trough. You see where it's this U shape. And we have some jet maxima or jet streaks coming in here. And so it's no surprise that, we're in a trough pattern and it's kind of cold. As I recorded this lecture video today, we were getting snow. So it all sort of connects together. And that's hopefully one of the things that you learn in this class is how all these different things in meteorology connect together, especially in how they contribute to severe and hazardous weather. So next up, we're going to connect that to the next scale down, synoptic scale, and I will see you soon for that.